Whew. Okay, now let's talk about the correctness of the binary search algorithm. So let's first form the predicate regarding our recursive function call. Now, since our recursive function call is sort of defined by the start and end arguments, we can form our predicate around that. So let's say the predicate is that the index of key is between start and end. So notice that for our algorithm here, it doesn't actually check for the end element. So since we set end as equal to n, the last element or the last index to be checked here should be n minus 1. So the index of key is actually will never be equal to n. So now we proved our predicate using induction. So for the base case, our start is equal to 0 and end is equal to n. Now, since index 0 is the first index of the list and the last index of the list is n, then if the index is indeed in the list, it if our key is indeed in the list, its index should be between start and end. So therefore, our base case is true or it holds. Now for the inductive step, now there are two cases or two different recursive calls that we get depending on the value of mid when compared to key. So when the value of the list at mid is less than the key, start becomes mid plus 1 and end is retained. So that means the key or the element we're looking for is in the upper half of the list. Now, since we know for a fact that key is less than end, since we assume uh, the predicate in its base form is true, then we can say this half of the inequality is true. And since we checked that key is greater than the element at mid, then we can safely say that mid is less than or equal to the index of key. So given this recursive call, the recursive call here, this one exactly, given this recursive call, the predicate still is true. Now, for the other one, the analysis is similar, since we know for a fact, given the base case of, given our predicate, assuming it to be true, start is always less than or equal to the index of key mid. Then, uh, since we've checked that key, the value of key is less than the element at the index mid, then we are sure that this part of the inequality is true. So what I think I forgot to say about the first case is that since our function called here is from key start mid, and now becomes mid, and therefore it is still true. So our predicate is true for both this case and this case. So we can say that after a recursive call, the predicate is still true. Therefore, our predicate is correct. So lastly, we check the results upon termination. So we have three cases for when the recursion or the loop terminates. So the first case is when there's exactly one element left in the partition. So when end minus start is equal to 1, it means that based on the predicate, the index of key can only be equal to start. So since, for example, if we end up with start being equal to, let's say, 2, and then, end equal to 2, start is equal to 1. So If start is 1 and then end is 2, then key can only be equal to 1. Now, since there's only one element, we can verify that. Now, given or using the conditional or the ternary expression here, when they are equal, we return the value of the index of start. So we found the element. Otherwise, we return -1, which means the element is not in the list. Then for this next case is when end is less than or equal to start, which means the partition is empty. Now, because the partition is empty, the index of key exists in an empty list. So therefore, the key does not exist in the list. So we return -1. Now, the more special case is when the key is apparently equal to the middle element of the list. So that's a special case, or most likely our best case, where we can stop the recursion early because we already found the element. So since the termination at each case behaves as expected and follows the predicate, we can conclude that the algorithm is correct.